Hello everyone, welcome to a new video. Today we're talking about depth first search. It's very important algorithm in AI and it also shows up in interview all the time. So let's dive deep into it. Let's start by looking into the graph. We have a root node and we have its children. We have a branching factor that is 2 in this graph. Branching factor is basically the number of children of the maximum number of children of every node. So let's number the graph. Now what happens in depth first search is it starts from a root node and the root node then asks its children. For example, in this case, it will ask its first child, that is number 2, are you the target node? So let's also define the target node. Let's say our target is, I don't know, just some X value. Okay. I will ask my first child, are you my target node? So, and in this case, it's not. Then I will say, okay, then carry on the search from yourself. So 2 will say, okay, I'm not the target. Let me look at my child. So in this case, 4, let's say that's also not the value. 4 will then look at its child, first child. Okay. In this case, 4, 5, 6, 7, it will be 8. And let's say, let's put it another X here. Okay. X is the second child of 4th. So X is the second child of 4th. So in this case, so first it will go to node number 8 and target, of course 8 is not equal to our target. Then 8 will look at its child and so on and so forth. And once all the children nodes of 8 are exhausted, that means all of its children are exhausted, then 8 will come back here and it will tell its parent node, I couldn't find any that matches the target value. Then 4th node will say, okay, let me look at my second child. So now it will look at its second child and it found the value 4. It found the X value. And then 4 will say, okay, I found my value. So I will just return true that I found the value. And node number 2 will say to root node, I found the value, and it will return back. So that's how you find a target value in depth first search. And now you must be saying that we were lucky in this case. We got a value here. What will happen if our value is, let's say, the rightmost value of the graph? Let's say, and that's a good question to ask. Let's say our value is here, that's X. In this case, we will have the worst time complexity. That means our algorithm will need to traverse all the number of nodes in this graph. So let's calculate the number of nodes in this graph. At level 1, we have 1 node. At level 2 or depth 2, actually this is depth 1, so we don't consider the root node as depth 1. That's basically depth 0. At depth 1, we have 2 nodes. At depth 2, we have 4 nodes. Do you see a pattern here? That's basically equal to 2, 0, 2 raised to power 1, 2 raised to power 2. And if we look more carefully, our branching factor was 2, right? We defined our branching factor 2. So the number of nodes at depth D is equal to, let me delete that. The number of nodes at depth D will be B raised to power D, right? You can just look at it from visually and see and derive that. So in our worst case, we would need to traverse all the number of nodes in this graph. Now, we just calculated the number of nodes at level D. What's the total number of nodes? Total number of nodes will be approximately p raised to power d as well, because we will need to do b1 plus b square and so on and so forth. That will be approximately b raised to power d. Now that's the total number of nodes, so that's basically our time complexity. What's is our space complexity? Now before we move to space complexity, another important point that I want to tell you guys is that there could be case when the depth differs, like every node have different depth, right? Let's say node number 3 has depth of 7 and node number root has depth of 9 and so on and so forth. In that case, we consider h to calculate the time complexity. H is the max depth of this graph, so it's an approximate value, and still the time complexity will be exponential, that is p raised to power h. Okay, so that's the time complexity. What's the space complexity? We always store the whole depth of our search, and how many nodes are in a depth d. For example, the maximum number of nodes that is possible at a depth d is d, right? We just traverse the depth, so that's the max number of nodes that you can store. So let's say you are starting from root, right? This is root, you go to node number, and this is 1, so you go to node number 2, node number 3, and so on and so forth. So that's the maximum number of node will be equal to d, your current depth basically of the algorithm. So let's say the max depth is h in your graph, so the space complexity will be O of h. Okay, all right. So now we have talked about the algorithm and how depth first search works. Now let's look into the code. So code is pretty straightforward. I have a class here that defines node, and that's not really important in this case. It's just a class to represent node. Depth first search class is the one that basically does the heavy lifting. It has a method that is called build graph, and its responsibility is just to build the graph. Giving a branching factor in depth, it builds a graph, and you can look into the code to find more about it, how it does that. It basically calls build child nodes using breadth first search. So I build the graph using breadth first search because it's easier that way, but you can build graph anyway. That's just my implementation. Let's look at the main algorithm here that is called search. What search does is it says, okay, give me a target node and I will traverse the graph and see if I find it or not. And it calls this self.findTarget. So let's look at self.findTarget. So findTarget says, okay, if the ID of my current node is equal to target node, then that means I found the node. I'll return true and path. Okay, path is just an extra variable that stores our current traversed path. It just stores every node that we have traversed till that point. The second check we do is if the depth is greater than equal to the maximum depth of the graph. If there's no nodes to be traversed, no nodes left to be traversed, then we just return false from there. Okay. Now this is the main part here. What we do is we say I'm at my current node and I have to look at all its children. Okay, for example, if I'm at the root here, from the root here, I will look at my current children, that is 2 and 3 in this case, node number 2 and node number 3. Okay, I look at my current child. So let's say child will be 2. So in this example, child will be 2 and 3. So I will say start the search from node number 2, that is the child. Okay, and see. Now let's say 2 will go to 4 and so on and so forth, and 4 of course has x here. 4 will return true. Okay, then I will say target found is true. If target found is true, then return target found. That means just return true to my parent also. So in that case, we don't need to traverse this part. From 5 we don't need to traverse at all. Okay, so this will return true, and 2 will return true to its parent, and then root will return the answer to us. Okay, and this is the variable path that keeps track of our current the current path that we have taken till now. Okay, so that was the algorithm. Take some time to digest it. It's not that complicated when you understand the graph visually and see what's going on. We go depth wise instead of breadth wise, so we go from left to right. That's another good way to remember it. We go from left all the way to right. So first we examine the leftmost, right? Then we examine this, then we examine this, and slowly we examine all the nodes like that. So I hope you learned something from it. I will publish the code on GitHub so that you guys can look at it. Please comment if you learned something valuable from this video. Also comment any future videos that you would like me to do. I will also attach a Google form that you can write your reviews in and write some topics that you would like me to do. That will really help me in deciding my next video. So please like and subscribe, guys, and I will see you in the next video.